The topic of our discussion today is polymers. This is the first series of polymers. This is Polymers 1. Let me go over the objectives first and discuss those with you. And before we can start, today I'm going to go over fundamentals of polymer science and technology, trying to introduce you to the different types of polymers, their structure, their chemistry, and some of their properties. We are going to talk about thermoplastic polymers. Of course, these objectives would apply to the entire series of polymers that we are going to cover. Not all of these objectives would be covered today. Objective number 3 is thermosetting polymers. Objective number 4, elastomers, and 5, talking about the recycling and biodegradability, or the ability to recycle polymers. So these are 5 main objectives of polymer series. In each part 1, 2, and 3, and we are going to cover some pieces, and in order to make the complete puzzle, we would take a look at different aspects of polymers throughout these topics. Let me start by talking about what a polymer is. The word polymer is derived from the Greek words poly, which means many, and meros, which, you know, the os being dropped, and it was reduced to mer. So polymer mean many mers, and mer really mean parts. So polymers made of there are molecules that are very long. We're going to take a look at those, and they made of they're very long, and they made of these different parts. Again, I'm going to take a look at those shortly. I don't want to deviate your attention to that yet. So we could have thousands, even millions of units in a single polymer molecule. In general, polymer is defined as a compound consisting of long chain molecules, each molecule made up of repeating units connected together, and most of them are carbon based, and therefore they're considered as organic chemicals. Not all of them, not some of the synthetic ones, but most of them. And so we're going to discuss polymers as the major topic of our discussion today. There are different types of polymers. They are public, pretty much divided into 2 types of polymers. They're familiar with plastics and rubbers. However, from the engineering point of view, and as engineering classification of materials, we divide them into 3 major categories of thermoplastic polymers, thermosetting polymers, and elastomers. The first 2, thermoplastic polymers and thermosetting polymers, they are what is commonly known as plastics, and the third one, elastomers, they're known as rubbers. Some examples: plastic bottles, and of course the bottle caps itself, and rubbers that are shown here. And the way we apply polymers, we usually do not use them in heavy type of a duty construction applications, although recently, for the past 30 years, they've been heavily used on the building pipelines, piping industry, and also used heavily for rehabilitation of some of the deteriorating structures that we have. Those are the main 2 categories of application that I can think of. So let's talk about thermoplastic polymers. Call it thermoplastics to abbreviate that. So throughout this lecture, I'm going to drop, in many cases, the word polymers, and I'm going to just use, for example, in this case, thermoplastics. What is thermoplastics? Remember, some of these words are used as plural, not singular, but I interchangeably use a singular verb is, or plural are, or was and were. So I want to make sure we understand that vocabulary first. So I might say thermoplastics is, or I might say thermoplastics are, and I use that interchangeably. So thermoplastics are solid materials at room temperature. They would become liquid when they're heated to temperatures of not like elevated temperature like steel, but only to a few 100 degrees. So you can have something to compare with. Of course, there are certain advantage to having a material with this kind of a character. If you're an engineer and want to work with the material, and you want to pick a material that has certain characteristics, you might try to look at thermoplastics because they are economical and they can easily be shaped into products. Can you imagine, instead of having water in plastic bottles, you could have them in steel containers? Of course, the cost would be much higher. There are also the problems of for example, rusting and other types of problems that are associated with other types of material. So one of the biggest advantage of plastics is they can easily be shaped into many different shapes that are desired, and it is also very economical. The other advantages, thermoplastics could be subjected to heating and cooling cycles. Of course, there is a limit to that heating and cooling cycle, and that would these cycles of thermal loading and thermal onloading could go on repeatedly without causing any significant degradation to the material. There are some, but they are not significant. And it's important to realize that, of course, that range of heating and cooling loading and unloading would be pretty much, it's not a large range. It's rather narrow. And in this course, we symbolize that, and by TP, and also the industry is also commonly referred to thermoplastics as a TP. So every time you are dealing with the material and you hear the word it's a TP, that means it's a thermal plastics material. So what about thermosets? What's the difference between thermoplastic and thermosets? Again, thermosetting polymers are called thermosets, and of course that's an abbreviation, and the singular and plural subject-verb agreement here, it also applies here. They cannot tolerate repeated heating cycles as thermoplastic or TPs can. When initially heated, they soften and flow for molding. As we are elevating the temperatures, we can produce a chemical reaction that hardens the material into a solid that is infusible. If we reheat that, then thermosets, unlike thermoplastics, they degrade, and it becomes, they char rather than soften. So it's very important to realize these characteristics of TP versus TS, which is a symbol for thermosets. Okay. And thirdly, let's talk about rubbers. There are polymers that exhibit extreme elastic extensibility. That's one of the major advantage of elastomers, or what is commonly known as rubbers. When they're subjected to relatively low mechanical stress. If you pull them too hard, if you stretch them too hard, they're going to break. Some people they compare elastomers or rubbers with character of some people. If you push them too hard, they may break. That's just a side note. Some elastomers can be stretched by a factor of 10 and yet completely recover to their original shape, meaning that if you let go of the force that pulled it, of course that force cannot be too high because it's going to rupture the rubber, but if you pull it by a factor of 10 and let go of it, then it would completely recover to their original shape. Remember that one of the advantages of steel was its ductility, in which we could pretty much in the um, elastoplastic range, we could pretty much stretch it. That is one of the was one of the advantages of steel. For rubber, that is true, not exactly at the same magnitude, but the load here is very different. In the case of steel, the magnitude of the load was much higher. But the property of elastomers also help us to apply them and use them in applications that is needed. Again, the best example is a rubber band or rubber itself, that you can think of many advantages of using that. Again, the elastomers, the properties of elastomers are quite different from thermosets, but the molecular structure is the same, and that is different from the thermal plastics that I just previously went over. What about the market share of pretty much the polymers? Well, thermoplastics are commercially the most important of all three others. The one that I discussed. About 70% by tonnage of all synthetic polymers produced are thermoplastics. Thermosets and elastomers, they share the remaining 30 almost equally, but thermosets maybe slightly over than 15%, maybe 15 point some, and that would bring down the remaining 50% of elastomers down to 14 point some. These numbers cannot be 100% accurate. There are approximation, and that's the best that is available to the industry as far as the market shares are concerned. If you look at the volume on a volumetric basis, the current annual usage of polymers they exceeds that of metals just by the volume and not the weight. The reason that we're comparing it this way is because thermoplastics are not heavy; they're light, and if you want to compare them based on the weight itself or the tonnage, of course they cannot compete with any other material. And some industries they compare it on a volumetric basis. You probably heard about some of these commercials on TV that the amount of plastics that we produce every year, we can do this and we can do that with that. While some of these commercials are true, there are also many of them they're one-sided. They don't tell the entire story. Many of them do, but many of them they don't. I can't say all of them are not true or accurate, but yes, the biggest problem that we have in engineering is that while we say one material is not good for the environment, we know that. However, what would be the alternative of not using that material? So unless we have alternatives, we have options, it is very difficult to say, for example, one material would harm the environment and others wouldn't. All material, they have environmental effects. One is more than the other, and one must always weigh the options, weigh the benefits against the the downside, and before one material can be used. Some examples of polymers of thermoplastics or TPs. They're one that's almost every engineering student is familiar with, and that is PVC, the polyvinyl chloride. PVC pipes are commonly used, and there are also polyethylene, and they're all also polystyrens and so on. Nylons are also another good examples of polymers. Examples of thermosets and epoxies. Many of these epoxies, they're thermosets. Also certain polyesters and all. So this would demonstrate a good difference between thermoplastics and thermosets in case of epoxies. And an example of elastomers, again, natural rubber is a good example. Also synthetic rubber, which exceeds the tonnage of natural rubber presently. Why polymers are so important and why are they applied as an engineering material, and we look at it as an engineering material? Well, I've already went over some of these. Plastics can be molded into different shapes. Some of these shapes could be really intricate parts, and we may not be able to make those using any other material. Usually it doesn't require a lot of processing or post-processing. They are very compatible with net shape processing on a volumetric basis. Polymers are cost competitive with metals. They generally require less energy to produce than metals. Certain plastics are transparent, which makes them competitive with glass in some applications. Also, it's important to realize that if it wasn't for polymers, some of these toys that we make for kids might not have been as safe as it is. If we want to make some of these toys out of any other material but polymers, we need to polish them and we need to apply them. One must realize the toy industry is a huge industry, and I know that because I have a young one. That's how I know about that. But most of you guys that have kids, you're familiar with that, and you know that many of these shapes that these toys are made of, it could be very difficult to make using any other material. We can make them out of other material, but it requires a lot of processing and polishing and what have you. Some general properties of polymers: they are low density. Of course, we need to compare them with another material. That's in comparison to metals and ceramics. They have a good strength to weight ratios for certain polymers. It doesn't apply to all polymers, but for certain polymers, the strength to weight ratio is pretty good. And the low density applies to almost all polymers relative to metals and ceramics. One of the biggest advantages of polymers, the biggest advantage of polymers, are their high corrosion resistance. And that's very important in the case of plastic water bottles and things like that, containers that would actually contain liquid, and they must be corrosion resistant. And They also have low electrical and thermal conductivity. That's another major advantage. In the case of thermal conductivity, very important. It could be used for some of the insulation materials and what have you, because they don't transfer temperature like some other material. That also goes in the case of electrical property, low electrical conductivity that they have. As with any other material, in this course we try to take the objectivity out of the application of material. Each material, as I've started on day one of the course, each material has its own advantages and disadvantages. Sometimes we cannot even really call them advantages or disadvantages. We need to look at the application first. What is it that we need to make? Then we would look at the material and we pick the appropriate material for the application. Some of these studies may take a while, but at the end it's important to realize when we pick a material to build something out of it. For the case of our engineering application, it's important to realize what is it that is used for and what are the design parameters, and before we can go ahead and pick the material. So polymers are no exception in this case. They have low strength relative to metals and ceramics. They have a very low modulus of elasticity if you want to compare them to metals and ceramics. They have low stiffness and the service temperature are not like steel or ceramics. They are limited to only a few hundred degrees, so they're not really made for extreme temperatures. Another limitation of polymer is their viscoelastic properties. This can be a distinct limitation in load-bearing applications. So that's why we don't make our buildings out of polymers, not yet. Maybe at some point the composite science gets so advanced that we can make them out of polymers, but of course they are not good in the applications in which we are looking for a load-bearing application. So that's what I mean. Is that really a limitation? Well, depends on the application. For something that we really are not going to use it as a load-bearing material, then we can look at polymers. If we are really trying to design for a material that has load-bearing applications, then polymers is not the name of the game. We need to avoid those. However, the application of polymers to some of these very strong materials, in the case of composite FRPs and so on, and they're applied on steel, they're applied on reinforced concrete, and they applied on different surfaces, and they also provide some major advantages as far as the rehabilitation costs and so on. And it is known that some polymers degrade when subjected to the sunlight and other forms of radiation. Steel is not like that. Metals are not usually like that. So it's important to realize that whenever that we have high exposure to sunlight for extended period of time, and then we need to think about if you want to apply polymers or not. So, so far we talk about the polymers, their properties, and so on. Now, how are they made? Almost all polymers, they're used in engineering. They're synthetic, and they need to go through a chemical process to make it. They're made by a chemical processing. They're pretty much synthesized by joining many small molecules together. Remember, poly means many and mers mean parts, so we always deal with these large molecules, very large molecules, and they're called macro molecules because of their size, and they are like a chain. Surely we're going to look at some of those structures. The smaller units they called monomers, okay, or monomers, and they're generally unsaturated organic molecules that consist of carbon and hydrogen. Best case is the ethylene C2H4. So let's take a look at the polyethylene. Here's an example of synthesis of a polyethylene from ethylene monomers or monomers. First, we have N ethylene monomers, and then we try to put them, have a long chain out of that. So from N number of those, we would go to a polymer structure of chain length N. So we put them pretty much right next to each other through the synthesis. The synthesis is going to cause them to be put right next to each other, N number of molecules, and that would give us the molecule, the long molecule with the length N that I just looked at. The process of polymerization is a chemical process. As such, we have two methods that we can use to synthesize the polymers. One is the addition polymerization, and the other one is the step polymerization. And very important to know those steps and the difference between the two. Every time we produce a polymer, it's generally associated with one or the other. So it's either addition polymerization or step polymerization. So let's take a look at each of them separately. Addition polymerization is the first one that we are looking at. In this case, the double bonds between carbon atoms in the ethylene, the monomers are induced to open up so they can join with other monomer molecules. There's no other way I could describe this to you except the sentence that I just read to you. Of course, there would be some connections, and they would occur at both ends of the expanding macromolecule. It's going to develop this long chain of repeating mers. Again, I bring your attention back to the name polymers, many mers, many parts. So, of course, we need to have some kind of a catalyst here. It's a chemical catalyst to open the carbon double bond in some of the monomers and make the process to occur. And this is called addition polymerization. In this case, some examples of polymers that are produced by addition polymerization is the polyethylene, and so on, and they're all listed here. And PVC is also another good example in which we use the process of addition polymerization. Again, in this process, there are double, bonds between carbon atoms. We are going to again induce to open so these molecules they could join with other molecules. And again, in this process, the double bonds between carbon atoms in the ethylene monomers are induced to open up so they can join with other monomer molecules. This is very important to know the definition. So an example is shown here. Each of these monomers are shown on on the one figure 1 here depicted here, there would be one initiation, one that would be initialized, and that would be pretty much other monomers that are going to join this one, and after a while, as we go through the process, of course, the chain would be longer and longer and longer, and eventually we're going to achieve number 3. All these mers, they join together through the molecular bond, and we are going to have a long chain of polymer molecule. What about step polymerization? Talk about the addition polymerization. What about step? In this form of polymerization, the two reacting monomers are brought together to form a new molecule of the desired compound. As we go through this reaction, as the reaction continues, there'll be more reactant molecules that be combined with the molecules first synthesized to form polymers of length N2, N3, N4, and so on. In this process, the polymers of length N1 and N2 can also be combined to form a molecule that's the length of that molecule would be N1 plus N2. So the two types of reactions are proceeding simultaneously at the same time. So, and examples of polymers that are produced using step polymerization is nylon, polycarbonate, and so on. So let's take a look at the model of a step polymerization. The model in part 1, this is A. You're going to have N mers, and we have a monomers, and then we're going to have the N mers and the monomer together. It's going to show as something like model as part 2. Then, as we are continuing this process, we are going to have N1 mer, and then we're going to have N2 mer of different length, are different. They're different. N1 and N2 is different, and then the end product would be N1 plus N2 mer. This is not a subtraction here. This is just N plus 1 mer, and this is N1 plus N2 mer. Okay, so don't be confused by this. This is like more like a dashed line, dash mer. Okay. What is a degree of polymerization? As I've discussed so far, the molecules in a given batch of polymerized material, they have different length. Okay, so we need to pick up a length that'd be N, and that's an average length for the batch, and this applies when the statistical distribution is normal. So the mean value of N is called the degree of polymerization. So if you could have a batch, and in that batch the polymerized length of the material is different. One is N1, one is N2, N3, N4, N5, and so on. If we draw the distribution for this batch and pick the length at random, pick a few N1 and a few N2 and a few N3 and so on, and then we draw the distribution, we would see that we are going to have a normal distribution. And for that normal distribution, the mean value of the length would be, we call that N, and that's called degree of polymerization, or DP, for each batch. Why do we think that that's important. Why do we study it? Because dP affects the properties of the polymers. If we have higher dP, that would increase the mechanical strength, but it also increases the viscosity in the fluid state, and that makes the process to be more difficult because it's just not as viscous as we want it to be and to work with. So the degree of polymerization is important because it would affect the properties of the polymer, most polymers, in such a way that higher dP would increase the mechanical strength, but it also increased the viscosity in the fluid state. The molecular weight of a polymer is defined as the sum of the molecular weights of the moles in the molecule. So, excuse me. So how do we define molecular weight? It is n times the molecular weight of each repeating unit, and because n varies for different molecules in a batch, of course the molecular weight would be a variable, and we need to somehow interpret this as an average. So this is an average molecular weight, and this is a degree of polymerization, which we already taken as the average. So if the for example, for different polymers, this is different. For polyethylene, and look at the difference between the two. Polyethylene, in polyethylene, we have the dP of 10,000 and molecular weight, average molecular weight of 300,000. As we're coming down for the PVC, it's 1,500, and the molecular weight is 100,000, almost 1/3 of this, and this is also reduced by a factor of 8 or 9, somewhat in that range. Nylon itself, now we see that the degree of polymerization is pretty low, only 120, and the molecular weight also goes down to 15,000 among the material that is commonly applied. And nylon has it's among the one with the lowest. I mean, this is depend on the application, but for common material that we use, nylon dP is 120. That's among the lowest, and molecular weight is also 15,000. That's also among the lowest. The polycarbonate, look at that one. The degree of polymerization is 200, but the molecular weight is 40,000. So again, it's important to realize how the degree of polymerization and molecular weight goes hand in hand, and how would they vary for different types of polymers. Not all, but for major categories. So the molecular structure of a polymer is also a note of examination here. Polymers, they're linear structures, as I told you, many MERS, they're chain-like, and that is the characteristics of a thermoplastic polymers. We also can have branched structures that can also be found in thermoplastic polymers. In this case, they're chain-like, but with side branches. And we can have cross-linked structures. They're not, in some cases they could be not as tight as we want it to be. It could be loosely cross-linked, or it's tightly cross-linked. If it's loosely cross-linked, that's a typical of elastomer characteristics. If they're tightly cross-linked, that's the characteristics of thermosets. An example of a polymer molecular structure, linear, branched, lightly cross-linked, and tightly cross-linked are shown here. A, it's no-brainer, it's linear, it's long. B, a no-brainer, it's branched, and it's also long, but with branches. Light cross-linked, they are like chains that have wider openings in between. Okay, I'm just crossing some of these openings for you to see. So they're still long, and they're like a net, but it's not tightly fit. So they're lightly cross-linked. And as the spacing becomes smaller, spacing between these molecules, they become smaller and smaller, then we would see that we get into the category of tightly cross-linked, and of course that would also affect the properties. So they're really pretty easy to see here the way it's been shown here. Okay, so let me see how I can move forward now, because there we go. So let's take a look at some of those effects that I just mentioned. The thermoplastic polymers are always have linear or branch structures, and sometimes the mixture of the two. So as branches increase, then we are going to have more entanglement among the molecules, and that is that's what makes the polymers. Of course, they're stronger in the solid state and more viscous at a given temperature. In the plastic or liquid states, that's the properties of those molecular structure that we just saw. And if they're cross-linked, what is the effect of cross-linkage on properties? An example are thermosets. They possess a high degree of cross-linking, and elastomers possess a low degree of cross-linking. And knowing the properties of those, you can see that if we have a high degree of cross-linking and low degree of cross-linking, the properties, characteristics of the material would be affected. The thermosets are hard and brittle, while elastomers are elastic and resilient. So high degree of cross-linkage makes the thermosets more hard and brittle, while when we have the low degree of cross-linkage, they are more elastic, more resilient, and more soft. Okay. Also, it's very important to realize the effect of cross-linking on the polymers to become chemically set. So it also affects the setting of the polymers. The reaction cannot be reversed. The chemically setting reaction cannot be reversed for polymers that have cross-linkage, and of course the polymer structures permanently change. If it heated, it cannot go back to its original properties. We cannot really recycle these. It would either degrades or burn rather than melt. I'm going to stop here for Polymers1 and continue with the topics that we started in the next recording. As always, feel free to send your questions via the course website to me, and we can discuss any questions that you have related to polymers. I hope you find these recordings very useful in your study. Thank you.